Welcome to the deep dive. Today, we're plunging into that really complex, fascinating world that, keeps everything digital running network technology. So whether you're maybe prepping for a tough technical interview or you're just curious about how it all works behind the scenes, well, you're definitely in the right place. Our mission today, it's really to cut through all the jargon, give you a kind of shortcut to understanding these critical networking ideas. We're looking at a curated list, actually, of top CCNP interview questions and answers. Covers routing, switching, security, the whole lot. Think of it like we're mining for the gold nuggets of knowledge, those little aha moments that make you think, okay, now I get it. Seriously, there's some foundational stuff here. Brilliant concepts. Really essential if you've ever wondered how a network actually, well, thinks.
Yeah, and what's really insightful when you look at these kinds of questions, it's not just what engineers know, it's
Yeah.
more about how they approach problems,
Yeah.
how they think about building systems that don't fall over, that resilience piece. It's about the smart design underneath.
I like that way of putting it. Okay, let's kick off then. Routing fundamentals. This is all about how data finds its way right through the network maze. And the first big distinction, probably the most basic one, is static versus dynamic routing.
Right, so static routing.
Yeah.
Think of it like manually typing in directions on a map for every single trip. You literally hard code the paths. It's simple, works fine for tiny networks where nothing changes much, zero overhead.
Hmm.
But yeah, it doesn't scale at all.
Right, yeah, because if things change and the network gets bigger, you need something, well, smarter. And that's where dynamic routing comes in. Protocols like OSPF, EIGRP, they automatically figure out the routes, they share updates, they interrupt if something breaks. I mean, can you imagine trying to update static routes for like a whole city's network, let alone the internet? It'd be impossible.
Totally impossible. A nightmare. And speaking of EIGRP, it's famous for its DUAL algorithm. That's the diffusing update algorithm. What's really clever about DUAL is how it guarantees loop-free paths. And this is key. It calculates backup routes ahead of time. It's kind of like having a backup plan already mapped out before anything actually goes wrong.
So it's not just finding the best way, it's already got plan B ready to go. Wow. You mentioned feasible successor routes. That's the pre-calculated backup you mean.
Yeah, exactly.
That sounds like it makes failover super fast then. Almost instant.
Pretty much near instant recovery, yeah.
Yeah.
That pre-calculation is the magic. And if you think bigger picture, these routing concepts, they're really what makes the internet itself work, how it heals itself when links go down. It's incredibly resilient, which brings us neatly to HSRP. That's the Hot Standby Router Protocol.
HSRP. Right, that tackles gateway redundancy. So like, if your main router connecting you to the outside world dies, you don't lose your connection. How did that work without all your computers needing new settings?
It's quite neat, actually. You have one router that's active, doing all the work, and another one just sitting there, the standby. They share a single virtual IP address. That's the address all your devices use as their gateway. So if the active one fails, the standby just takes over that virtual IP seamlessly. Your devices don't even notice. Very common for important networks.
That's really clever. Proactive design. Okay, now OSPF, another big dynamic routing protocol. It has this DRBDR election thing on certain networks. Why do you need a designated router and a backup? Why don't all the routers just talk to each other directly?
Good question. Imagine a network like an office Ethernet switch where maybe dozens of routers are connected. If every single one tried to form connections and swap full updates with every other one, it would just be chaos. So much redundant chatter, really inefficient. So the DR and the BDR act like designated speakers for that network segment. They collect and distribute the updates, reduces the noise significantly. The election itself, it looks at the OSPF priority first, higher wins. If that's tie, then it's the highest router ID.
Okay, so it's about efficiency, keeping things organized. Makes sense. And OSPF uses different LSA types, link state advertisements. What are those about in simple terms?
Think of LSAs as like different pages in the network's blueprint or map. A type 1 LSA, it's a router describing itself and its direct connections. Here I am, here are my links. Type 2 is the DR describing the network segment itself, who's connected to it. Type 3 is for summarizing routes between different OSPF areas, keeping things manageable. And Type 5 LSAs, they advertise routes learned from outside OSPF, like maybe from another routing protocol or the internet. Each type adds a piece to the puzzle.
Got it. Different map layers, essentially. And then there's this concept, sounds kind of weird, floating static route. Static but floating? What's the deal there?
Yeah, it sounds a bit odd. But the floating part is key. It's basically a static route you configure, but you give it a higher administrative distance. Remember administrative distance, or AD. It's like a trustworthiness score for route sources. Lower is better, more trusted. So by giving the static route a high AD, maybe like 254, you make sure the router only uses it if the main route, say, one learned via OSPF with an AD of 110, disappears. It floats above the primary route and only kicks in as a manual backup if needed. Doesn't interfere otherwise.
Oh, that's a really smart trick for backup without messing with your dynamic routing. Okay, understanding how networks choose paths.
Yeah, that's absolutely vital. So routing gets data between networks, but what about moving data efficiently within a network? That's switching essentials, right? And a classic point of confusion here, VLAN versus subnet. Oh yeah, definitely a common one. So VLANs, virtual local area networks, they operate at layer 2, the data link layer. They basically chop up a physical switch into multiple separate broadcast domains, like creating virtual walls inside the switch, devices in different VLANs. They can't directly hear each other's broadcast traffic.
Okay, layer 2 segmentation. And a subnet is layer 3, the network layer.
Exactly. Subnets are about organizing IP address ranges, logical addressing.
And the really flexible part is they don't have to map one-to-one, do they? You can have like multiple VLANs in one subnet, or one VLAN stretching across different subnets if you route between them.
Precisely. That flexibility is huge for network design. And these layer 2 things, especially VLANs, they're foundational for keeping networks stable and letting them grow, particularly in big companies. But when you start segmenting things, you also risk creating loops if you're not careful. And that's where STP, the spanning tree protocol, becomes absolutely critical.
STP, the loop preventer, keeps the network from collapsing in on itself, basically. It stops traffic going round and round forever by blocking extra paths, right? How does it pick which ones to block?
You got it. Loops are bad news. They'll just grind a switch network to a halt.
There.
STP's job is to find those redundant physical paths and logically block some ports. It starts by electing a root bridge, which is like the central reference point for the network topology. Then all the other switches figure out their single best path to that root bridge. Any other paths that would create a loop, those ports get put into a blocking state.
So it allows for physical redundancy. The backup cables are there, but it only lets one logical path be active at a time until something fails.
Exactly. Intelligent redundancy. But, the original STP, it could be a bit slow reacting when things changed, like really slow.
Yeah, I've heard that, which is where RSTP comes in. Rapid spanning tree.
Absolutely. The rapid is the key word there. STP might take, 30 to 50 seconds to figure things out after a link failure? Yeah. That's an eternity in network time. RSTP, it can often converge in under, say, 6 seconds, sometimes even faster. Huge difference for keeping things online. It streamlines the port roles and states compared to classic STP, which helps make it much, much quicker. Wow, 50 seconds versus 6. Yeah, that's significant. Okay, so when we connect devices like PCs or printers to these switches, we talk about trunk versus access ports. What's the difference there? Simple distinction, really. An access port is typically for an end device, your computer, your IP phone, a printer. It belongs to and carries traffic for just one specific VLAN, the trunk port. It's usually the link between switches, or maybe between a switch and a router. It's designed to carry traffic for multiple VLANs all at the same time.
And it needs a way to keep that traffic separate, right?
Yeah.
That's the tagging, like 802.1Q.
Exactly that. 802.1Q tagging puts a little label on each frame as it crosses the trunk, saying this belongs to VLAN 10, or this is for VLAN 20. That's how the receiving switch knows where it goes.
Makes sense. And to manage all these VLANs across a bunch of switches, there's VTP, VLAN Trunking Protocol.
Yeah, VTP. Its main job is to make life easier for network admins. Instead of manually creating VLAN 10, VLAN 20, VLAN 30 on every single switch, you can use VTP to automatically propagate that VLAN information across your network, across a VTP domain.
Sounds handy. Does it work in different ways?
It has 3 main modes. Server mode is where you actually create, change, or delete VLANs. That's the master copy. Client mode switches just listen to the server and update their own VLAN database accordingly. They can't make changes themselves. And transparent mode. Those switches don't participate in VTP directly. They don't update their own database from VTP messages, but they do pass the VTP messages along to other switches. They're just like a clear window.
Okay, different roles for different needs. Good stuff. Another key thing for switch performance and reliability is Ether channel. What's the problem that solves?
Bandwidth and redundancy between devices, usually switches. Imagine you need more speed between 2 core switches than a single gigabit link can provide. Or what if that single link fails? Ether channel lets you bundle multiple physical links, 2, 4, 8, whatever, and treat them as one single logical link.
Ah, so you get the combined speed of all the links, and if one cable in the bundle gets unplugged or fails.
The traffic just automatically redirects over the remaining active links in the bundle. No interruption, usually. Plus, it load balances traffic across the links.
Nice. Best of both worlds, speed and backup. And there are protocols like PHP or LACP that manage that bundling automatically.
Exactly. PHP, Cisco proprietary, LACP is the industry standard. They negotiate the channel formation between the switches.
Cool. So yeah, switching, it's all about intelligently connecting devices, keeping things segmented with VLANs, avoiding those nasty loops with spanning tree, really the bedrock of the local network.
Yeah.
Okay, let's shift gears now. Let's talk network security and core fundamentals, protecting the network and making sure data flows well.
Absolutely critical stuff. It's amazing, really, how many layers of security and performance tuning go into modern networks. They're not just dumb pipes.
Yeah.
And a really fundamental security tool is the ACL, Access Control List.
Right, ACLs, the network bouncers, filtering traffic. What's the main difference between standard and extended ACLs?
Think of it like this. A standard ACL, usually numbered 1 to 99, is basic security. It can only look at the source IP address. Where did this packet come from? That's it. An extended ACL, numbers 100 to 199 and higher ranges too now, is much more sophisticated. It can check the source IP and the destination IP and the protocol like TCP or UDP, and even the specific port numbers like port 80 for web traffic. So much finer control over exactly what traffic you allow or deny.
Okay, yeah, much more granular. Got it. Then there's NAT, network address translation, hugely important, especially because we ran out of IPv4 addresses. How does NAT work its magic?
NAT is essentially an address translator. It lets devices with private, internal IP addresses communicate with the public internet. There's static NAT, which is a permanent one-to-one mapping. Like this specific internal server always uses this specific public IP address. Good for servers you need people to reach from outside. Then dynamic NAT. It uses a pool of public IPs. Internal devices grab one from the pool when they need to go out, then release it back when done. First come, first served. But the most common type, the one pretty much every home router uses, is PAT, port address translation, also called NAT overload. This is the really clever one. It lets many internal devices share a single public IP address. It does this by keeping track of connections using different port numbers. That's what saved the day for IPv4.
That PAT overloading. Yeah, sheer genius, really. Allows millions of home networks to function with just one public IP each. Okay, so beyond the edge, what about securing things inside the network? Like securing a switch port where a user plugs in. What tools do we have there?
Oh, several important ones. Port security is a big one. It lets you restrict which MAC addresses, which specific devices are allowed to connect to a port, or limit the number of devices. Stops random people plugging things in. Then BPDU guard. This protects your spanning tree. You enable it on access ports, and if it ever receives an STP BPDU message, which should only come from other switches, it shuts the port down. Prevents someone plugging in a rogue switch and messing up your network topology. And storm control. This stops a faulty device or a loop from flooding the network with too much broadcast, multicast, or unknown unicast traffic. It basically puts a rate limit on that kind of potentially disruptive traffic.
Right, stops one bad actor from taking down the whole segment. And one more I know is crucial. DHCP snooping. What does that guard against?
DHCP snooping is all about preventing fake DHCP servers. Imagine someone plugs in a little wireless router from home, and it starts handing out bad IP addresses to your corporate network.
Yeah.
Chaos. DHCP snooping lets you designate which switch ports are trusted, where your real DHCP server is connected, and which are untrusted, like user ports. It filters DHCP messages coming from untrusted ports to block those rogue servers. Ensures clients only get valid IP info.
Okay, so it protects a core network service. Very important. All right, shifting down a layer almost. The fundamental transport protocols. TCP versus UDP. How do they differ? It's a classic comparison.
It really is. They're the workhorses of Layer 4. TCP, Transmission Control Protocol, is like sending a package with tracking and delivery confirmation. It's connection-oriented, it sets up a session first, and it's reliable. It guarantees delivery, makes sure packets arrive in order, and retransmits anything lost. Think web browsing, HTTP, email, file transfers, FTP. You need all the data to get there correctly. UDP, User Datagram Protocol, is more like sending a postcard. Or maybe shouting across a room, like you said.
Okay.
It's connectionless, just sends the data without setting up a session. And it's best effort or unreliable. No guarantees, no retransmissions if something gets lost. But it's much faster and has less overhead. So it's great for things where speed matters more than perfect reliability, like DNS lookups, streaming video, voice over IP calls. Losing one tiny packet in a phone call isn't usually a disaster.
Perfect analogy. Registered mail versus a postcard. Got it. And for devices figuring out who their neighbors are, we have CDP and LODP.
Right. Discovery protocols. CDP is Cisco Discovery Protocol. As the name implies, it's Cisco's own thing. Works great between Cisco devices for sharing info like device model, software version, connected port. LODP is Link Layer Discovery Protocol. That's the important difference. It's an industry standard, i.e. standard. That means it works between equipment from different vendors. Dill Switch can talk to a Juniper router, which can talk to a Cisco phone using LODP. So in today's mixed environments, LODP is generally what you want to be using.
Ah, interoperability wins again. Makes sense. Okay, looking ahead, the big one. IPv4 versus IPv6. We know IPv6 has way more addresses, but what else is key?
Well, the address base is obviously the headline act. IPv4 is 32-bit addresses. We just ran out. That forced us into using NAT everywhere. IPv6 uses 128-bit addresses. The number is just astronomical. Billions upon billions per person. So the primary need for NAT for address conservation anyway basically disappears. Every device can potentially have its own unique public address.
That's a fundamental shift, and the header's different too, simply in some ways.
Yeah, the IPv6 header is actually larger 40 bytes fixed compared to IPv4's 20 bytes plus options, but it's fixed and more streamlined. Some fields from the IPv4 header were removed or moved to optional extension headers. The idea is that routers processing the packets only need to look at a simpler fixed header, which can speed things up. It's designed for more efficient processing.
Interesting. So potentially faster routing. Okay, and finally, making sure the important traffic gets through when the network is busy. QoS, quality of service. What's the main goal there?
The main goal is fairness, but really it's about prioritization. When your network link gets congested, and they often do QoS, make sure that the traffic you care about most gets preferential treatment. Think of a highway during rush hour. QoS is like creating an HOV lane or an emergency vehicle lane. Your critical apps, like maybe a video conference or a VoIP phone call, get to use that fast lane. While less time-sensitive stuff like a big file download or email might have to wait a bit in the flow lanes, without QoS, everything just gets stuck in the same traffic jam, and your call quality turns terrible.
So it stops, like a big download killing your Zoom meeting. How does it actually do that? What are the mechanisms?
It's usually a multi-step process. First, you need to classify the traffic, identify what it is. VoIP, video, web browsing, file transfer.
Yeah.
Thinking. Mark it, usually by setting some bits in the IP header, like DSCP values, to signal its priority level. Next comes queuing. Switches and routers use different queues for different priorities. High priority traffic goes into queues that get serviced first or get more bandwidth. And finally, you might use shaping or policing. Shaping smooths out traffic bursts to conform to a certain rate, often used on outbound traffic. Policing is stricter. It just drops traffic that exceeds a defined rate, often used inbound. It's all about managing bandwidth allocation based on priority.
Wow. Okay. What a tour. Seriously, from how data finds its path with routing to how devices link up via switching and then layering on all that security and optimization, we've covered a ton of ground. Understanding these pieces, even at this level, it really does feel like a shortcut to grasping how networks actually operate day to day.
Absolutely. And having this knowledge, it's invaluable, whether you're in a technical discussion, trying to understand why something's designed a certain way, or honestly, just curious about the infrastructure that powers so much of our modern world. These aren't just abstract ideas. They're the real nuts and bolts, the clever solutions that make it all work together.
So thinking about all this, what does it mean going forward? You know, networks are getting more complex, more distributed, cloud, AI, all that. Here's something to chew on. Which of these fundamental building blocks we discussed today, routing, switching, security features, protocols like TCP, UDP, which ones do you think will become even more critical in the next 5 or 10 years, and why? What's going to be absolutely essential for future network design?